So here's an example on the screen of just writing the symbolic form for P, you build it, Q, they will come. So you'll see several examples that I've walked through. Take time now to pause the video and work yourself through those examples. All right, so once you've done that, let's look more into some related statements with implications. The converse, inverse, and contrapositive. So you will see on your screen that the converse, not the school, the converse is if Q, then P, which is written Q, the arrow P. If Q, then P. The inverse is if not P, then not Q. The contrapositive is if not Q, then not P. So you'll see the notation for all of those off to the right. You need to make sure that you just know which one is which. So for instance, in the example below, it says to write the inverse. You need to be able to look at this chart and come up with the inverse. So this is one chart that I would highlight in my notes because you do need to know this. So let's look at one of these examples. The completed notes will be posted on D2L that you can go back and fill in the blanks that I'm skipping on the video. So here's my example. For each of the following implications, state the converse, inverse, and contrapositive. So here's my statement. If x equals 3, then x squared equals 9. So P is going to be that x equals 3. Q is going to be that x squared equals 9. So the first one says to find the converse. Well, the converse is, like I have right up above, Q, then P. If Q, then P. So, in my example, it would be if x squared equals 9, then x equals 3. If Q, then P. The next one, the inverse, is if not P, then not Q. If not P, then not Q. So for this example, it would be if x does not equal 3, then x squared does not equal 9. Not P, then not Q. The last one, the contrapositive, if not Q, then not P. So if not Q, Q is x squared equals 9. So then if x squared does not equal 9, then x does not equal 3. So let's look down. Which of these original statements was basically the same? All right, so let's look at some theorems going along with this idea of implications. So my first theorem is theorem 2.2 out of your book, and it says that the implication, if P then Q, and its contrapositive, which says not Q, then not P, are logically equivalent. That is, if P then Q, that thing means logically equivalent. So if P then Q is the same thing as this. They are equivalent in the study of logic, which is what we're doing. So 2 more or 3 more rules that we're going to cover, and then the whole next video will be a bunch of examples. So the law of detachment. The law of detachment says that if P then Q is true and P is true, then Q must be true. So what that really just says is if you can say that the whole implication is true, both pieces must be true. So notice I'm breaking down that if P then Q is true, which here's my symbol, then P in itself and Q in itself must be true. Okay, the next one, law of denying consequent. If P then Q is true and Q is not true, then P is also not true. So now we're kind of going backwards. So the first one said, the law of detachment, top one, says that if P then true is true, then P and Q must be true. If P then Q is not true and Q is not true, then P is not true. Okay, and then the last one, my chain rule, says that if P then Q, if P then Q is true, and if Q then R is true, then I can say that P all the way to R is true. That's what the chain rule says. So, this is very similar to the transitivity property, which says if A equals B and B equals C, then A equals C. So that's kind of how it relates. You've seen that in some other math classes. So pick back up in the next video, and we're going to run through a whole bunch of examples.